Hi, folks. We are looking at section 6 of chapter 3. That's Newton's 3 laws of motion. Okay. The first law, you know it, it's inertia. And it is all about the tendency of objects to resist motion. And what that law says is that any object is going to continue moving however it's moving at the same speed in the same direction unless and until something comes along and puts a force on it, pushes or pulls it. Okay? An object will keep moving just as it's moving unless you push it or you pull it. Okay? That's inertia. Seems simple, right? I'm going to stay seated in this chair unless somebody comes along and shoves me out of it. Easy, right? Here's where we start getting confused, I think. Newton's second law. You learned that as acceleration equals force, and we'll say net force over mass, right? So that is A equals F net over M. Newton's second law, okay? The acceleration of an object depends upon the force applied to it and the mass of the object. The bigger the force, the more the acceleration is going to be. The bigger the mass, the less the acceleration is going to be. You're going to spend some time in class tomorrow. Actually, by the time you see this, it'll make sense to say you spent time in class today exploring how that relationship works. But here's what I really want you to get. I want you to start thinking about Newton's second law as really not a whole lot different from Newton's first law. In fact, you can think of Newton's first law as a special case of Newton's second law. Inertia is just a special example of this second law. Let's see how that works. Let's go back to our definitions. Acceleration, that's change in motion. That's speeding up, slowing down, changing direction. Okay? And Newton's first law of inertia says an object's motion will not change. An object won't speed up, it won't slow down, it won't stop, or it won't change direction. Won't speed up, it won't slow down, it won't change direction. In other words, it won't accelerate unless a force, a non-zero net force, acts on it. Okay? So, in other words, acceleration, where net force equals 0, if net force equals 0, what's acceleration? 0 over mass. Doesn't matter what the size of the mass is, right? Whenever you have a fraction whose numerator is 0, what's the value of that fraction? 0. So, where net force equals 0, acceleration will be 0. Now, we need to stop here for a quick moment and explore what that means. That does not mean that the object will be still. Doesn't mean the object's going to stop moving. It feels that way to us. It seems that way to us because we live in a world in which there are always forces acting on objects, right? We think, oh, if I stop pushing this mouse, it's going to stop moving. Because that's what happens in our real world. The reason that happens is because we have friction and we have gravity. Pretend, when you're thinking about Newton's laws, pretend you're in outer space. Pretend everything is in outer space. Okay? And if I push, see if I can get the table. If I push this mouse on the table, it's going to stop moving when I stop pushing. That's because of the friction between the mouse and the table. If there were no friction, when I stop pushing this mouse, it should just keep going at the same speed in the same direction as when I pushed it. That's what the law of inertia says. It doesn't say the mouse will stop moving when I stop pushing it. It says the mouse's motion will remain unchanged if I stop pushing it. If there's no non-zero net force acting on it, if there's no push or pull, the motion of the mouse won't change. So if the mouse is still, the mouse is going to stay still. If the mouse is moving and no force is acting on it, the mouse is going to keep moving same direction. What does it take to change the direction of the mouse? A non-zero net force. What does it take to slow the mouse down? A non-zero net force. Oh, we've got a convenient one here. We call it friction. Okay, so please keep in mind, when acceleration is 0, that does not mean the object is not moving. It just means the object's motion is not changing. The hard thing about the law of inertia is that you have to pretend you're in a world you're not in. You have to pretend that you're not experiencing gravity and friction all the time in order to sort of get it. Or you have to be able to imagine, to identify the gravity and the friction that are happening on your object all the time. And that's, of course, why we studied gravity and friction before we studied Newton's laws of motion. So, Newton's second law of motion says acceleration equals force net, that is the net force acting on the object, divided by the object's mass. Newton's first law says if the net force is 0, the acceleration is 0. That's inertia. Okay? There's one other thing that I want to clear up. When I've been giving you problems, much of the time you have been assuming that acceleration equals 9.8 meters per second squared. Okay? 9.8 meters per second squared is one special case of acceleration. That is the acceleration due to gravity on Earth acting on an object. So acceleration equals 9.8 meters per second squared whenever we are talking about dropping something, free fall. Then acceleration is 9.8 meters per second squared. The acceleration of that pen, 9.8 meters per second squared. The acceleration of my clipboard, 9.8 meters per second squared. When we are not talking about free fall, do not assume acceleration is 9.8 meters per second squared. You're going to have to move to, unless I tell you what acceleration is, if we're not talking about free fall, you're going to have to figure it out. Okay? And in this area, you can use this formula. Acceleration equals force divided by mass. And there's one very last thing that I want to do to help relate three things that we have talked about, right? Okay. Remember, 1,000 years ago, we did the speed triangle. Okay? We can say that speed is distance divided by time. We can say that time is distance divided by speed, and we can say that distance is speed times time. Okay. Then we learned about acceleration, which by definition is a change in velocity, a change in speed, or a change in direction. And we said, this is pretty special. We said acceleration is we said acceleration equals speed divided by time, like meters per second per second. Okay, acceleration is speed divided by time. We can get time by taking speed and dividing it by acceleration, and we can get speed by taking acceleration and multiplying it by time. Acceleration times time is speed. Okay, let's look at our new one. Hello! We can do this too, right? Acceleration equals force divided by mass. Mass equals force divided by acceleration, and mass times acceleration equals force. So we now have 3 of these rate triangles. Keep that in mind. All right, I'll see you. Let's see, for me it's Sunday. You'll be seeing this on Monday. So I'm going to say, I'll see you tomorrow, and I'm also going to say, it was good to see you today. Right, bye-bye.